Okay, guys, welcome everybody. I'm Badia Srestha. I'm chairing this afternoon session with Dan Kurjewski. Once again, of course, this is a mechanical aerospace engineering senior design presentation conference. Of course, now, of course, without any delay, I want to, of course, give this virtual, let's say, presentation floor to our team. Okay, guys, you can start now.
All right, thank you. Hello, my name is Josh Rios. My partner is Logan Kucherik, and today we're going to talk about our project, the design of a Formula SAE electric induction system. The first thing we're going to do is talk about the rules that exist in the Formula SAE competition regarding forced induction, and also outline the parts of a forced induction system. Next, we'll establish the design metrics for our project and talk about what we want our project to do and why we think it's important. Then we're going to talk about the MATLAB simulation we created to verify the validity of the performance metrics we came up with and to prove their feasibility and impact on the Formula SAE vehicle. We will then go into the GT power simulation part of our project and talk about how we were able to test various compressors virtually without having to physically build a test bench. Once we determine the compressor, we were then able to size an electric motor and suitable battery pack size. Finally, we will talk about our design, show it in a vehicle assembly, and talk about the next steps. To begin, let's talk a little bit about what forced induction systems are and the two major types that exist. Forced induction systems are systems fitted to a vehicle that increase the intake charge density coming into an engine. This is done by compressing intake air through the use of a compressor. By forcing more air into a cylinder, more fuel can be added, and therefore the engine can make more power. The two main types of forced induction systems are the supercharger and turbocharger. The difference in these systems is where the input energy to spin the compressor comes from. In a supercharger, the compressor is driven using a belt, which is spun by the crankshaft of the engine. This means that the speed of the compressor increases as the engine speed increases. This has an advantage of having relatively small amounts of input lag compared to a turbocharger. The downside of that is that it takes away engine power to spin. A turbocharger, on the other hand, is powered by the exhaust gases coming out of the engine. It uses the exhaust energy to spin a turbine, which is connected to a shaft to the compressor. A turbocharger has the advantage of not being powered off the engine directly, so any energy used to spin the compressor is powered off waste heat that would otherwise have been exhausted into the atmosphere. The downside is that a turbocharger takes an amount of time to build boost, so there's a bit of lag between the application of the throttle and the turbocharger producing boost. The scope of this project is to produce a system for use on the WMU Formula SAE vehicle. It will be designed, built, and tested for this particular vehicle in mind. We will be limited by our budget, as several of the components can be quite expensive, as well as lab access protocols preventing us from doing much physically in the labs on campus. Our project centers around the WMU Formula SAE vehicle, and as such, there are a number of rules to follow to ensure the system complies with the rule book and is legal for competition. The Formula SAE rules stipulate that an intake restrictor must be used, and the size of the restrictor is based on the type of fuel. In our case, a 19mm intake restrictor is mandated because the team runs E85. This is comparable to the size of the diameter of a penny that all air entering the engine must pass through. In addition, there's a certain sequence of component placement that must be followed. The correct rules-compliant sequence is the restrictor, the compressor, throttle body, the intercooler, and then the engine. Finally, for our project, it's important to know the rules regarding electricity flowing through the car. The electrical system we use is limited to a maximum of 60 volts and must be wired through a master kill switch. When we were starting the project, we looked at a number of different technical papers and past project reports from researchers and students from other schools. From this, we were able to get an idea of the types of systems that have been tried in the past and see what worked and what didn't. From these papers, we were able to narrow down the list of suitable compressor candidates to a small handful that could work for our engine size and with our particular rules restrictions. Furthermore, we were able to learn a lot about the implementation of a forced induction system on a similar engine type and built to the same rules we're constrained by. To begin our project, we took a look at what we thought were important aspects of the design and what would be most beneficial to the team. We focused on 4 different forced induction setups: a traditional turbocharger, a traditional supercharger, an E-turbo running exclusively off battery power, and an E-turbo running off of electricity harvested from exhaust gases by a turbine. We then broke down into how well we thought on a scale of 1 to 5 each system would meet design criteria seen on the left. Once we rated each system in each category, a weighted total was found to determine the best system. As you can see, we determined that an e-turbo in any configuration was better than both a traditional supercharger and traditional turbocharger. The only difference between the two e-turbo setups was that the e-turbo plus a turbine offered slightly lower weight, since the energy needed to run the system would be harvested with an alternator connected to the turbine, which would weigh less than the weight of the necessary batteries to provide enough power for the endurance run. Ultimately, however, the increased complexity of integrating a turbine and alternator and managing the battery charge level was prohibitive to our project, since neither Logan nor I have experienced that level of electronic systems. As such, we decided to go with a battery-powered e-turbo for our design. Once we determined the type of system we wanted to use, we came up with the specific performance targets and design outcomes we wanted to accomplish. First and foremost, we wanted to increase torque in the lower RPM range to facilitate fast acceleration out of low and medium speed corners. Our goal was to increase torque by 8 foot-pounds below 5,600 RPM to extend the flatness of the torque curve lower in the engine speed range. We also wanted to increase the peak power from 89 to 100 horsepower. The Formula SAE competition is partly made up of an autocross course, the defining feature of which is a large number of very tight corners and slaloms. By increasing low-end torque, we would be allowing the vehicle to accelerate at a higher rate and thus complete the course more quickly. Ultimately, more points are scored at the competition the faster you complete each event, so this would have a positive effect on our score. Next, being able to control how much boost we are producing allows us to change the behavior of the engine from event to event. It can also be changed to match a driver's skill level and comfort. In the Formula SAE competition, there are points available based on how fuel efficient you are. Being able to change from maximum performance to a more fuel-efficient driving mode would allow the vehicle to maximize the number of points it can score in each event, maximizing the overall score. By increasing low-end torque, the lap times are reduced as well. In this case, lower lap times equals more points. Finally, since much of the project was completed virtually, we were able to create a useful GT power simulation that can be used by future project and Formula SAE teams to further investigate this project as something to be implemented in the car moving forward. In previous years, the team has taken the car to be tested on a chassis dynamometer. This gives us a baseline to use to compare the effect our system has on the unmodified vehicle. In addition, a GT power simulation created by the team was validating using this data. The vehicle in its stock form produces 89 horsepower at 11,600 RPM and 41 foot-pounds of torque at 11,600 RPM as well. As you can see, the torque curve is relatively flat, which is a desirable attribute that we're hoping we can keep. However, as you can see, the torque doesn't really pick up until around 5,600 RPM. Our goal is to change that. First, we wanted to see that increasing lower end torque would in fact have a positive effect on the vehicle performance. To do this, we created a torque curve that was in line with our design goals. In blue, you can see the original torque curve from the dyno, and in orange, you can see the proposed torque curve. The orange curve comes up to a constant torque much earlier than the original torque curve, signifying an increase in low-end torque. Then, from about the middle of the engine speed range on, the torque curves are the same, since the behavior of the torque curve after the initial pickup was deemed to be acceptable. Once that torque curve was created, a degree 6 polynomial line of best fit was applied to each torque curve to get a characteristic equation to use to calculate the torque at any given RPM. We got R-squared values of 0.9795 and 0.9924, which indicate very strong correlations. The MATLAB simulation itself is relatively straightforward. First, a series of functions reads in vehicle data from a spreadsheet. The spreadsheet has information regarding gearing, tire sizes, aerodynamics, and more. The relevant data points are read into the simulation and stored as constants. The equations for the lines of best fit found above were put into the MATLAB program within a while loop. The while loop keeps track of engine RPM and calculates the torque at each given RPM. The RPM values start at 4,686 RPM and ends at 12,686 RPM. This is because the dynamometer data we have corresponds to these engine speeds as its lowest and highest speeds. Once the function calculates the torque at the given RPM, the wheel torque is calculated. This simulation is a point mass simulation that uses the engine torque to calculate the available tractive force at the tire and thus maximum possible acceleration at each RPM. The time to run through the entire RPM band is kept track of to give us a time to compare. For the purposes of this simulation, it was completed in first gear and no shifting was done. The graph shows the time taken to run through a distance corresponding to traveling the circumference of the tire multiplied by the engine RPM. And the modified engine curve gives us a faster time, 58 versus 65 seconds, demonstrating that increasing low end torque will give the vehicle a performance advantage on track. Next, it is very important to understand the behavior of the airflow through the restrictor. Since there must be an intake restrictor fitted to the vehicle, we can calculate the maximum amount of air that can flow through the restrictor, and thus the maximum amount of air that can be ingested by the engine. Choked flows are conditioned in fluid mechanics whereby the local velocity of the airflow through an orifice reaches the speed of sound. At this point, air behaves as a non-compressible fluid, and thus the air cannot be compressed anymore. This has the effect of putting an upper limit on the amount of air that the engine can induct, regardless of the actual amount of air the engine could induct without the restrictor. To determine the mass flow rate at which this phenomenon occurs, the following information from NASA is used. Specifically, we're using the second equation, used when flow is considered choked. Using temperature and pressure data sourced online, the average air density of the testing facility at WMU and the competition sites at Michigan International Speedway and Auto Club Speedway were found. This air data was used since these are the competition sites in North America, as well as the place the team tests the car. This gives a more realistic value for mass flow since it uses real-world conditions the team expects to see. Then the mass flow is calculated using a temperature range of 50 to 110 degrees Fahrenheit. This is also a realistic expectation of the range of temperatures that could be seen by the vehicle based on historic weather data. The overall average choked mass flow rate for our forced induction system was found to be 8.8 pounds per minute. This gives us a target mass flow rate for our forced induction system in a way of screening turbochargers and superchargers that will not work based on the flow rates found on their compressor maps. Assuming 100% volumetric efficiency, choke flow would happen around 11,000 RPM. This is verified by choke flow calculations the team has done previously, as well as conversations had with members of other Formula FSAE teams who run the same engine that we use.
So GT Power is the industry standard engine performance simulation software. Our physical engine has been tested against the simulated model to ensure its accuracy. The naturally aspirated model was provided by WMU FSAE. GT uses a graphical interface like LabVIEW to represent individual components. Our FI system, shown above, fits right here in the engine model, right behind the intake restrictor. Beginning with the simple compressor node, a proof of concept could be established. The node is meant to be utilized in the early stages of development when no compressor map has been established. It allows the user to produce trends like a turbocharger, but without all the necessary data. The simple compressor showed promising but incomplete results, and it was time to move on to an actual compressor. In place of a turbine shaft input, a simulated prescribed angular velocity is utilized via the speed boundary rotation node. The speed boundary, therefore, would drive the compressor at any specified speed. Because of the small 600cc engine utilized in the FSAE vehicle, a comparably small compressor must be selected. The GT12 by Garrett is sized for engines up to about 130 horsepower, and one of its most appealing aspects is its availability and very low cost. They can be readily found for about $250. The GT12 was tested at shaft speeds of 150,000 and 175,000 RPM. These selected values allowed the mass flow rate to be nearest the 8.8 pounds per minute, while also maintaining the turbo's highest compressor efficiencies, near 70 to 76%. At a shaft speed of 175,000 RPM, there is 10 horsepower and 30 foot-pound gains over the baseline. Once issues with motor selection, or electric motor selection from using a direct drive system came about, further compressor analysis was completed using geared superchargers. We'll discuss more on the electric motor selection later. So the Roadtrack C1516 has a gearbox ratio of 12.67. So at 140,000 RPM at the impeller, we have an input shaft speed of 11,050 RPM. Much better for electric motor selection. Tests were completed at impeller speeds of 110, 20, 30, and 40,000 RPM. As impeller shaft speed was increased, peak power increased while also shifting lower into the RPM range. Each increase in impeller RPM predictably raised peak horsepower by 3 or 4, with the largest horsepower examined to be 101.16 horsepower. Most impressively, the torque curve showed the desirable flat lines across most of the RPM range of the engine, while still providing an excellent raise in peak torque. This would conclude our compressor selection, and now we can move ahead to find a suitable motor. recall that we opted to use a supercharger because of the shaft speed issue with the GT12. So the original plan to utilize an existing off-the-shelf turbocharger for cost savings and simplicity did not foresee the issues with motor selection. The main areas of concern are the high RPM of the input shaft and its torque requirements, along with motor cooling and balancing. The maximum torque was tested against each case of the simulation, which corresponds to an engine RPM. Case 1 is an engine RPM of 4,686 RPM, and case 9 is approximately 12,000. The maximum observed torque on the compressor input shaft is very deceptive. While values of 0.16 to 0.2 foot-pounds may seem incredibly low, when you're turning at speeds more than 200,000 RPM, there are power requirements of 4 to 5 horsepower to turn that shaft. So utilizing the original design concept presents many issues with motor failure too. Electric motors cannot sustain speeds of 200,000 RPM for any extended period of time. A very extensive liquid cooling system would need to be implemented to prevent the bearings from melting, and if it faltered for even seconds, motor failure would be imminent. Furthermore, any deviations from perfection in construction of the coupling device would instantly surface at 200,000 RPM, and the motor could potentially vibrate or melt itself to destruction. So, brushless motors are most commonly found in manufacturing or hobby applications. The main disadvantage of the industrial grade motors is that they're often overbuilt for the application, and not often is weight considered as a design factor, and the motors often end up a little too bulky and a little too heavy for consideration in this design. For use with the Roadtrack C15, the APS 63100S boasts an impressive 5.4 foot-pounds of torque and is sized slightly above the 3.75 kilowatt requirement at 4.5 kilowatts. Operating with 200 kV, the main operating range is 9,500 to 10,500 RPM, which is the closest available with our load requirements. So only lithium polymer LiPo batteries were considered for this design. By choosing a 14-cell LiPo at 58 volts at peak is available to the motor. This remains below the FSAE regulated 60 volts for ICE engines. At peak draw, the motor draws 64.5 amps, and we found a 14S 5,000 milliamp hour battery that's perfect for this application. They can be wired in parallel to provide more capacity, and is only recommended to purchase 3 or 4 of these batteries for initial testing, as total turbo runtime has not been established, nor will be without bench and track testing, especially in the endurance event of 30 minutes. At lower than peak draw of 50 amps sustained for 30 minutes, 25 amp hours of battery capacity will be necessary. And that's about 20 pounds of battery, which is a lot. So for our motor, most ESCs available for the 14-cell LiPo applications are more than suited to handle the peak draw of 65 amps. To match the final motor selection, we selected a comparable Alienware ESC. As previously discussed, also tunability and usability are critical design metrics of the operation of this compressor. A Raspberry Pi would allow such controls to be implemented, as it can process an incoming signal from the engine RPM and then appropriately configure an output to the compressor motor. While the program necessary to run it will take many iterations to properly configure and test, it's certainly going to produce worthwhile results. So here's our final design utilizing the Roadtrack C15 and the Alienware APS 63100. And as you can see, a redesign of the intake is necessary to package the compressor a little bit more appropriately. So this project has been awarded a scholarship of $750. Although as the project progressed, it was clear that this would not satisfy the initially estimated financial needs. The largest updated costs were the cost of the supercharger over a turbo and the need for more and larger batteries. So the purpose of this project was to investigate the feasibility of an electrically driven forced induction system for a Formula SAE vehicle. We saw that the desired performance characteristics could have been achieved with an electrically driven supercharger. By simulating the addition of the components via MATLAB and GT Power, it is seen that engine performance is greatly enhanced and meets the specified design metric of the project. Our original goal was to expand torque by 8 foot-pounds at RPM ranges below 5,600 RPM, and we've exceeded that by over 20 pounds over the desired. So we also exceeded our desired peak power of 101 horsepower by 1 horsepower. not too bad. With further testing of a physical model on the chassis dyno and the track, the electric forced induction system could prove its worth in wins for the WMU FSAE team. Unfortunately, due to both budget and workplace constraints in place because of COVID-19 protocols, we were not able to build and test our system on an actual vehicle. We envision the next steps as being able to physically build the system and then test it on the vehicle. The testing would be able to verify the system's function and see how much of an effect on the performance of the vehicle it would have. It would then be important to further tune and optimize the system for each individual event. Furthermore, an intake redesign to accommodate better packaging and a blow-off valve as a safeguard against overboosting the engine is needed. Also, because we use LiPo batteries, a rigid impact-proof battery box would need to be constructed and separated from the driver by the means of a firewall, and while also being readily accessible to the safety and pit crew. Special training and policies need to be in place for safe handling, and fire extinguishing practice would need to be administered for use with these batteries. Most importantly, we'd like to thank Dr. Fajardo for all of her help, her patience, and really great insight on this project. We'd also like to thank Dan Wainwright, the powertrain lead of WMU SAE, and the GT Suite technical support, and Sean Harnish for their very fast replies and helping us out throughout this project. Thank you. You guys have any questions?
Okay, thank you, presenter. Now the presentation is open to the questions and comments. Please, anybody has a questions, unmute your mic, or please type on the chat room. So meantime, I want to ask a question, guys. What do you learn new skill from this project?
One of the biggest skills was it was sizing components, and then GT Suite was the one tool that we have not had very much experience with using. Yeah. So because GT Suite is so specialized for industry, there's not a lot of available tutorials or data out there to learn how to use it. So we had to effectively communicate with GT Suite through their phone and email, and then while also being able to articulate ourselves in a way that would give not the impression, but at least, you know, so we knew what we were talking about, and then be able to go backwards and work on our project with their recommendations.
Yeah, and we started this project, you know, back in September, and at the time, I was taking internal combustion engines, and then this semester taking engine design. So this project was a really neat way to be able to, you know, apply everything that I'd learned, like in theory and theoretical, into an actual physical product.
Thank you. So any other question to our presenters, please? Unmute your mic, and of course you can ask question directly, or you can type, let's say, in the chat room.
I'd like to add the one thing that we spent a lot of time on was getting a motor selection right with it. We spent a lot of time researching turbos beforehand, and that was the idea all along. And it was a rather late design change that we had to go to using a supercharger, because when it came to selecting a motor to work for the turbo, it was something that we thought was feasible in the beginning, and it was not for any lack of foresight, but the technology just isn't there yet to have a motor spin that high of RPM for that long. So it was a really important design factor in our project when we were done.
Yeah, thank you.
Hey guys, can you hear me okay?
Yes, sir, we can hear you.
This is Steve Perry. I'm with Ford Motor Company in electrified propulsion systems. Great project. It looks like, you know, good technical deep dive, as well as a lot of fun. I'm a big fan of Formula SAE programs. My question is, did you do any calculations about the efficiency of the electric forced induction? That is, the actual electric energy versus the gain in power from the engine itself.
Yeah, so one of the big considerations too with using our supercharger was the gearbox. We had a gearbox efficiency in between the impeller and the shaft. So the gearbox itself has an efficiency of 97%. Mm-hmm. And then we start, because of we ended up, by using the turbo, we ended up raising our peak thermal efficiency of the engine, because now we're making use of a little bit more stuff, and we were theoretically limited to about 91 horsepower already. So by adding this system, we raised it up to 101 horsepower.
Yeah, because if you do all of your mass flow calculations based on a 30% thermal efficiency, you hit a ceiling at around 91 horsepower, which is something that we calculated. And then in talking to other teams that have run forced induction systems and other teams in Formula SAE, that was the value that they had calculated as well. So we were able to increase our thermal efficiency by using a forced induction system, in theory in GT Suite. So that's something that we'd be testing once we were able to build a physical model, put it on a vehicle, and then take it to a dyno just to verify that the increase that we saw was something that wasn't manifested by something in the software, but it was an actual physical phenomenon.
Mm-hmm. That's really great. I'm just wondering if combined with a regen braking system, so that you can recapture some of your vehicle energy, store that in a battery, and then use that stored electrical energy to drive your turbo, which really enables you to burn more fuel.
Yeah.
But overall, would that be a net performance gain?
Yeah. So, like we said earlier, one of the I guess initial ideas we had was, instead of only using the compressor side of the turbo, was also using the turbine, and then instead of physically connecting the turbine and the compressor like they normally would be, we would connect the turbine to an alternator. That way we wouldn't have to store all of the energy up front that we needed, and we'd still be able to harvest the rejected energy from the exhaust gases. That way, our battery pack can be a little bit smaller, and we can even increase our thermal efficiency even more because we're using all of that energy. So
Right.
in order to do something like like regen braking, that would move us into a different category of formula competition. That would move us into a hybrid competition, which isn't what we do.
Right.
So I guess in terms of something similar to that would be where we would use the turbine connected to an alternator.
Yeah, great stuff. And I think with that exhaust turbine, that would allow you to remap your boost independently of engine RPM.
Yeah.
Yep. And that was the original goal, is theoretically we could have 100% boost at 0 RPM if we really wanted to. We didn't want them specifically. One slide in particular here, this one, where you can see the peak power as the impeller speed is increased, moves backwards. But theoretically, we could ride this black line at 140,000 RPM all the way up, and then we could start tapering back impeller speed and ride the peak pretty much all the way right across.
Yeah. So you could make a lot of gains in terms of drivability for the different driver skills you talked about.
Exactly.
Anyways, great project. Good luck in your careers, gentlemen, and thanks to your professors as well. Appreciate it.
Thank you very much, Mr. Perry.
Okay, guys, that's the last question we can take, I think. Thank you very much for the presentation.